In 1995, astronomers made a gamble that changed humanity's perception of the cosmos forever. They pointed the Hubble Space Telescope at what appeared to be the emptiest, darkest patch of sky they could find. A region in Ursa Major, so devoid of visible stars that colleagues called it a waste of precious telescope time. For 10 consecutive days, Hubble stared at this void, collecting photons that had been traveling through space for billions of years. When the image was finally assembled, it revealed not emptiness, but abundance. Over 3,000 galaxies crammed into a patch of sky no larger than a grain of sand held at arm's length. The Hubble Deep Field didn't just show us distant galaxies. It proved that the universe's apparent darkness is an illusion. Every shadow hides countless suns. Every void thrums with ancient light too faint for our eyes to perceive. Now, nearly 3 decades after Hubble's revolutionary glimpse into the cosmic depths, a new instrument has shattered every record for deep space observation. The European Space Agency's Euclid telescope, in just 1 week of observations, has captured images containing over 26 million galaxies, nearly 10,000 times more than Hubble's original deep field. But this isn't just about numbers. Euclid has photographed light that left its sources when the universe was less than 4 billion years old, catching galaxies in their violent adolescence, witnessing the cosmos when it looked fundamentally different from today. This is the deepest, most comprehensive image of the universe ever captured. And it's about to transform our understanding of everything. The scale of Euclid's first data release defies conventional comprehension. The images span a patch of sky 300 times larger than the full moon, an area so vast that if you held your fist at arm's length, it would barely cover a corner of what Euclid captured in a single observation. Within this cosmic canvas, the telescope has detected objects as faint as magnitude 29.5. That's 600 million times dimmer than what the human eye can see under perfect conditions. To put this sensitivity in perspective, Euclid could spot a candle flame on the moon from Earth, or detect the heat signature of a human body from beyond Neptune's orbit. Each pixel in these images contains more information than entire astronomical catalogs from just a generation ago. The clarity of these deep-field images transcends anything previously achieved in wide-field astronomy. Perfect Einstein rings, those cosmic mirages where distant galaxy light bends around massive foreground objects, appear as pristine circles, their light having traveled for 10 billion years before being gravitationally sculpted into these celestial halos. Intricate galaxy clusters reveal themselves not as simple collections of stars, but as dynamic battlegrounds where thousands of galaxies dance in gravitational choreography, some colliding in slow-motion catastrophes that will play out over hundreds of millions of years. Most remarkably, Euclid has captured the faint filaments of the cosmic web itself, the largest structure in the universe, a network of dark matter and gas that connects every galaxy to every other galaxy across billions of light-years, visible here for the first time in such exquisite detail. But Euclid's purpose extends far beyond creating beautiful images or breaking records. This telescope was built with a singular, almost impossible ambition: to reveal the invisible universe. While other telescopes show us what's there, Euclid is designed to show us what isn't, or rather, what we can't directly see, but know must exist. Its mission is to map the hidden architecture of reality itself, to trace the scaffolding of dark matter that holds galaxies in place, and to measure the mysterious dark energy that's tearing the universe apart. Euclid isn't just observing space, it's conducting a cosmic census of everything that exists, seen and unseen. Here's the disturbing truth that keeps cosmologists awake at night. Everything you've ever seen, touched, or imagined, every atom in your body, every star in the sky, every planet, moon, asteroid, and dust particle in the cosmos accounts for only 5% of the universe. This isn't speculation or theoretical hand-waving. It's observational fact confirmed by multiple independent lines of evidence. The periodic table, that masterwork of human understanding that catalogs all known elements, describes just 1/20th of reality. The other 95% remains fundamentally alien to our experience, invisible to our instruments, yet undeniably present through its gravitational and expansive effects. Dark matter, comprising approximately 27% of the universe, is the cosmic puppet master pulling invisible strings. We've never seen it directly. It doesn't emit light, doesn't absorb light, doesn't reflect light. It's not made of atoms as we understand them. Yet its gravitational influence is everywhere. Without dark matter's invisible embrace, galaxies would fly apart like untethered merry-go-rounds. The Milky Way rotates so fast that visible matter alone couldn't hold it together. Dark matter provides the missing gravity. When we observe galaxy clusters, we see them bending light from more distant objects, gravitational lensing that reveals far more mass than we can account for with visible matter alone. Dark matter isn't just present, it dominates the cosmic landscape, outweighing normal matter 5-to-1. Even more mysterious is dark energy, which accounts for a staggering 68% of the universe's total energy density. Discovered in 1998 through observations of distant supernovae, dark energy represents the most profound mystery in physics. It's not a force in any conventional sense, but rather a property of space itself, an intrinsic pressure that causes the universe to expand at an accelerating rate. Imagine throwing a ball upward and watching it not just fail to fall back, but accelerate away faster and faster. That's what dark energy does to the universe. Every second, new space is created between galaxies, pushing them apart with ever-increasing speed. In the far future, this acceleration will isolate every galaxy in its own observable universe, each one alone in an expanding void. Dark energy isn't just shaping the universe. It's determining its ultimate fate. To tackle these cosmic mysteries, Euclid began its journey on July 1, 2023, lifting off from Cape Canaveral aboard a SpaceX Falcon 9 rocket at 11:12 a.m. local time. The launch was flawless, the rocket's 9 Merlin engines generating 1.7 million pounds of thrust to escape Earth's gravitational well. But Euclid's destination wasn't orbit around Earth. Instead, it traveled for 30 days to reach Sun-Earth Lagrange, point 2, L2, a gravitationally stable position 1.5 million kilometers from Earth, 4 times farther than the Moon. This cosmic parking spot offers unique advantages. It's far from Earth's atmospheric interference and light pollution, maintains a stable temperature for the sensitive instruments, and allows continuous observation without Earth or Moon blocking the view. Euclid joins an exclusive club at L2, sharing this prime astronomical real estate with the James Webb Space Telescope, the Gaia Observatory, and the Spectre RG X-ray telescope. At Euclid's heart lies a 1.2-meter Korsch telescope, a 3-mirror design that delivers exceptional image quality across an unusually wide field of view. The primary mirror, made from silicon carbide, maintains its shape to nanometer precision, despite temperature variations. This isn't just about size, though 1.2 meters is respectable. It's about optical perfection. The mirror's surface deviates from its ideal shape by less than 10 nanometers. Smoother relative to its size than Earth's surface would be, if our planet were shrunk to a billiard ball. Light collected by this mirror follows a precisely calculated path through the telescope, bouncing off the secondary and tertiary mirrors before reaching the focal plane, where it splits into two channels, feeding Euclid's twin instruments. The visible instrument, VIS, is Euclid's sharp eye, a camera of extraordinary capability designed specifically to detect the subtle distortions that reveal dark matter's presence. Its focal plane consists of 36 CCDs arranged in a 6x6 grid, each one containing 4,000 x 4,000 pixels, a total of 609 megapixels dedicated to capturing the visible universe. But these aren't ordinary pixels. Each one measures just 12 micrometers across, allowing VIS to achieve a resolution of 0.1 arcseconds, sharp enough to distinguish between two candles separated by just 1 meter from a distance of 20 kilometers. From its perch at L2, free from atmospheric distortion, VIS captures images 4 times sharper than the best ground-based telescopes. This clarity is crucial for detecting weak gravitational lensing, the slight warping of galaxy shapes caused by intervening dark matter. While VIS provides the sharp images, the near-infrared spectrometer and photometer, NISP, adds the third dimension, distance. Operating in infrared wavelengths from 900 to 2000 nanometers, NISP can see through cosmic dust that blocks visible light and detect the heat signatures of the universe's most distant galaxies. Its primary function is measuring redshift, the stretching of light caused by cosmic expansion. As galaxies race away from us, their light shifts toward the red end of the spectrum, and the amount of shift tells us precisely how far away they are. NISP can simultaneously measure redshifts for thousands of galaxies, building a three-dimensional map of cosmic structure. It's equipped with 4 filters and 2 grisms, combination gratings and prisms, that spread galaxy light into spectra, revealing not just distance, but also chemical composition, star formation rates, and galactic ages. The true genius of Euclid lies in how VIS and NISP work together. VIS captures razor-sharp images showing galaxy positions and shapes. NISP measures their distances and properties. Combined, they create something unprecedented, a 3-dimensional map of billions of galaxies spanning 10 billion years of cosmic history. This isn't just a static map, but a time machine, showing how cosmic structure evolved from the universe's youth to today. By comparing galaxy distributions at different epochs, Euclid can trace dark energy's influence on cosmic expansion. By analyzing how galaxy shapes are distorted by gravitational lensing, it maps dark matter's distribution. Together, these instruments transform 2-dimensional images into 4-dimensional space-time maps. After reaching L2, Euclid underwent months of meticulous calibration. The first test images, deliberately out of focus, helped engineers fine-tune the telescope's optics. Temperature sensors monitored thermal stability, while star trackers ensured pointing accuracy to within 75 millarc seconds, equivalent to hitting a specific window on the International Space Station from Earth with a laser pointer. Engineers tested every filter, every detector, every mechanical component. They characterized how the instruments responded to different light levels, mapped dead pixels, calibrated color response, and measured optical distortions. This painstaking process ensured that when Euclid began its science mission, every photon would be accurately recorded and every measurement precisely calibrated. Euclid's science operations officially commenced in early 2024 with observations of 3 carefully selected regions: the Euclid Deep Field North in Ursa Major, the Euclid Deep Field South in Fornax, and the Euclid Deep Field Fornax centered on the Fornax galaxy cluster. These weren't random choices. Each field was selected for specific properties: minimal foreground contamination from Milky Way stars, year-round visibility from L2, overlap with previous deep surveys for comparison, and diverse cosmic environments from empty voids to dense clusters. These fields serve as Euclid's proving grounds, regions where the telescope will return repeatedly over its mission, building ever deeper observations that will eventually detect galaxies at the very edge of the observable universe. In just 7 days of observing these three fields, Euclid collected more data than most telescopes gather in years. The raw numbers are staggering but become truly meaningful when contextualized. Those 26 million galaxies detected in the first week? If you examined each one for just 1 second, it would take you 300 days of continuous observation to see them all. The data volume, 260 terabytes, would fill 50,000 DVDs or stream Netflix in 4K for 13 years straight. But it's not about quantity, it's about quality. Each galaxy is measured with such precision that astronomers can determine its shape to better than 1% accuracy. Crucial for detecting the subtle distortions caused by dark matter lensing. Here's the astounding reality. Everything Euclid captured in this first data release, those 26 million galaxies, those perfect Einstein rings, those cosmic Webb filaments, represents just 0.4% of the total sky area the telescope will survey over its 6-year mission. It's like judging the entire ocean from a single cup of seawater. If this tiny fraction revealed so much, imagine what the full survey will uncover. By mission's end, Euclid will have observed 15,000 square degrees of sky, catalogued 1.5 billion galaxies with photometry, measured spectra for 30 million galaxies, and created the largest and most accurate 3D map of the universe ever constructed. The Euclid Deep Field North, highlighted in the constellation Ursa Major, offers our clearest view yet into the universe's adolescence. This field was strategically chosen to overlap with legacy observations from NASA's Spitzer Space Telescope, allowing astronomers to combine Euclid's visible and near-infrared data with Spitzer's mid-infrared observations. The synergy reveals hidden treasures: dusty, star-forming galaxies invisible in optical light, ancient elliptical galaxies whose light has been traveling since the universe was 1/3 its current age, and gravitational lenses that magnify even more distant objects. In this field alone, Euclid detected 12 million galaxies in 1 week, including several candidates for galaxies formed less than 500 million years after the Big Bang. Euclid's superpower isn't just seeing distant galaxies. It's detecting how their light has been subtly bent during its journey to us. This weak gravitational lensing is barely perceptible. Galaxy shapes are distorted by typically just 1%, but Euclid's exquisite resolution makes these tiny distortions measurable. By analyzing millions of galaxy shapes, astronomers can reconstruct the distribution of all matter, dark and visible, between us and those distant galaxies. It's like deducing the shape of a lens by studying how it distorts the image behind it, except the lens is made of dark matter spread across billions of light years. This technique will allow Euclid to weigh the universe, determining exactly how much dark matter exists and how it's distributed. By measuring galaxy distances across cosmic time, Euclid is reconstructing the universe's expansion history with unprecedented precision. This isn't just about confirming that the universe is expanding. We've known that since Hubble's time. It's about measuring exactly how the expansion rate has changed over billions of years. In the early universe, gravity was winning, slowing the expansion as matter attracted matter. But around 5 billion years ago, dark energy began dominating, accelerating the expansion. Euclid's measurements will determine this transition period to within 1% accuracy, potentially revealing whether dark energy is truly constant, Einstein's cosmological constant, or varies over time, quintessence, a distinction that will determine the universe's ultimate fate. Perhaps Euclid's most visually stunning achievement is capturing the cosmic web, the largest structure in the universe. This vast network of dark matter filaments connects every galaxy to every other galaxy, creating a cosmic spiderweb spanning billions of light years. Previous observations could only hint at this structure, detecting the brightest galaxies at the nodes where filaments intersect. Euclid sees the filaments themselves, traced by dim galaxies and intergalactic gas. The images reveal a universe that's far from random. Galaxies align along these invisible highways, flowing like traffic on cosmic freeways. This structure, predicted by computer simulations but never directly observed at this scale, confirms our understanding of how gravity shapes the universe while raising new questions about the processes that light up these cosmic threads.